Welcome back. Today we're doing a little bit of a more difficult problem for Newton's second law involving more than one tension component. So if you didn't check out the last video, I showed you how to do common tension problems where you have blocks tied together with ropes or masses hanging from the ceiling. This is kind of the boss level. So if you can solve this problem, you should be very set for any AP physics class or any statics class in college or physics 1 in college. So let's get right into this. So we have a ceiling here holding two ropes, tension 2 and tension 3, one at 60 degrees, one at 30 degrees. They are tied to one rope, which we're going to call rope 1, and that is holding a 10 kilogram mass suspended in the air, and the entire system is in equilibrium. So what we are trying to do is we are trying to find tension 1, tension 2, and tension 3. So as shown in the previous videos, I'm going to split this up into three different systems. So we have, I'm going to call this system 1. This will be 2. This will be 3. That just helps for free body diagrams. All right, so I'm going to go ahead and start my free body diagram 1. That'll be just a system 1. Technically, it's not system 1, system 2, system 3. It is all one system, but it's three different parts of a system, so you can ignore the system. But that's just me being technical. All right, let's draw a free body diagram. We have our element. We have its weight force being mg, and we have T1. I'm going to write T1 in this case because the three tensions are not equal, because it's three different ropes. If they were all one rope, it would be equal, but because it's three separate ropes all tied together here, you gotta separate the tensions. So this is my free body diagram for um, the first section, and I'm going to draw my coordinate system, super important, like this for my free body diagram. So from here, using Newton's second law, and as you see, only the y direction, there's only components in the y direction, so I'm not going to worry about x. I'm going to say sum of forces in the y is equal to m1 times a. However, we know the system is at rest, so we get rid of this side. So we have tension 1 minus mg is equal to 0, and this just gets us tension 1 is equal to mass 1 times g. Tension 1 is equal to 10 times 9.8, which is just 98 newtons. So off the bat, we can quickly solve for tension 1 because it's just vertical, and because we took just this component of the whole system, it becomes like a simple normal problem. Now let's get into the tricky part 2 and 3. So we know that at the center, the knot, the forces are T2 goes up and left, T3 goes up and right, T1 goes down. But because the knot is in equilibrium, that means acceleration in both the x and y direction is 0. So I can say the sum of forces in the x is equal to 0 because mass times acceleration in x is 0, and sum of forces in the y is equal to 0. So there's no acceleration. It is a statics problem. So if you are taking a statics class, that is what that means. If you are in physics class, you'll get there in college, or you'll get it too later. But all this means is there's no acceleration in the x or y direction. All right, so let's break T2 and T3 into their components. But before we do that, let's draw a free body diagram for 2 and 3. So free body diagram 2. Actually, no, because there's no mass here, so we won't do that. We're just going to break apart the components. So for T2, we have the x component to be T2 cosine 60. And where I get that is if we just take, actually I'm not going to draw it in the center, I'm going to draw it here. Right, so this 60 and this 60 here are equivalent. So this is our x component, this is our y component for 2. So our x component would just be T2 cosine 60, and our y component, we'll call x2, y2, is equal to T2 sine 60. And we can do the same thing for T3. So we see that, I'm going to draw it down. So this 30 is equal to this 30. So we have the horizontal component of T3 would be, this is x3, this is y3. So the horizontal x3 would be T3 cosine 30. And then the vertical component is T3 sine 30. All right. Now that we have split these angles into verticals and horizontals, which correlate to our coordinate system, we can write equilibrium equations for this. So we know that the sum of forces in the x direction has to equal to 0. So our sum of forces in the x direction, so I'm going to rewrite that. So sum of forces in the x, we have, so our x3 goes to the right because these tensions are this way. So this tension force is to the right and up, and tension 2 is to the left and up. So our positive x would be T3 cosine 30 minus T2 cosine 60 is equal to 0. So we get T3 cosine 30 is equal to T2 cosine 60. And plugging in the values for cosine 30, cosine 60, we get T3 times 0.866 is equal to T2 times 0.5. And I'm going to rewrite this in terms of T2. So get T2 is equal to 1.732 T3. So this is going to be one of our first governing equations because, again, we are trying to solve for T2, T3. And we got this all from sum of forces in the x direction is equal to 0. So let's do the same for the y direction. Sum of forces of y is equal to 0. And this is sum of forces total. So we're going to have to include tension 1 as well. So we have, I'm going to say, because both y2 and y3 point upwards, so they're in the positive direction, while t1 is in the negative direction. I'm going to write this is equal to t2 sine 60 plus t3 cos, t3 sine 30 minus t1 is equal to 0 because there's no acceleration. So let's rewrite this a little bit. We'll have t2 sine 60 plus t3 sine 30 is equal to t1. Let's go ahead and plug in our known values. So this becomes 0.866 t2 plus 0.5 t3 is equal to 98. And this is our second governing equation. Now let's substitute each and solve for t2 and t3. So I'm going to replace t2 with 1.732 t3. So we'll get, so I'm going to write substitute. So we get 0.866 times 1.732 t3 plus 0.5 t3 is equal to 98. Using algebra and combining like terms, I'm going to skip this step, but this comes out to be t3 is equal to 49 newtons. Yeah. Now we take t3, plug it back into one of our governing equations. So we'll get t2 is equal to 1.732 times 49. So we get t2 is approximately 84.9 newtons. And there you go. So we can do a quick check with this just to make sure the vertical components equal 98 as to this governing equation. If we do 0.866 times 84.9 plus 0.5 times 49, let me just plug that into my calculator. Yep, and we get 98, so that works out. So there you go. That is how we solve these types of problems where we have more than one tension rope. Always draw your free body diagrams, split it into 3 or however many components you need. Draw your coordinate system, very important. Solve for or simplify everything in terms of x and y, and then go about it via substitution. And hopefully that helps. Again, this is a super, super common question you will see on AP exams, on statics exams, on physics exams. So please make sure you are familiar with this topic. And I'll see you next time.